direct comparison. It gets much more complicated to factor in these connecting flights because there are additional factors beyond price, like possibility of missing the connection, you or your luggage, or other inconveniences, overall time of travel, and so on, which is not really captured by a simple metric structure, right? So the thing that I want to talk about is a little bit more than a graph. So you have your airports and you have your flights, which give you the graph. And of course, as I said, between any 2 points, x and y, you have a direct comparison. So you have almost a metric. Of course, this metric is not separated because different flights might have the same price. And also, I don't look at flights beyond a certain level. If it is, say, more than $5,000, then it's close to infinity, and I admit that value as well. But as I said, the thing that we don't capture is the inconvenience of connecting flights versus direct flights. So what I want to look at is a comparative function between flights, connecting flights x, y, z, and direct flights. And what I like to assume is that, am I jumping too fast? Oh, I was jumping too far. OK, so I have objects, airports, I have these flights, I have the thing that is environmentally right, stay grounded, do nothing, and I have this metric, and I have this. So now let's go to this comparator. So condition 1 is clear. If you stay grounded at y, then the function that captures the difference is 0. And here comes a kind of strange condition. So you go in stages from x to y, y to z, z to w, and you might have direct flights between x and z, and y and w, and x and w. And what I want is, if you look at the sum of the differences here, and the difference between this part and that part should not exceed the sum of this, geometrically. Now, if you forget for a moment the direction, then we can draw this also as a tetrahedron. And the tetrahedral inequality in a tetrahedron says that the area of one side cannot exceed the sum of the 3 other sides. So this is sort of, the left-hand side is an interpretation, an algebraic interpretation of the right diagram. And let me tell you where this comes from. It's very old. So the Vienna mathematician and logician Karl Menger in 1928 had a paper on n metrics. So n metrics look at not the metric between 2 points, but you have n plus 1 points. Gale revisited those and examined the case n equals 2. That's where we have the tetrahedral inequality. So the other important ingredients for me is enriched categories, introduced by Allenberg and Kelly. Bill Lovier's milestone paper on metric spaces, to consider a metric space as a small category where the distance from x to y is interpreted as a Hom set. Okay? It's not a set, but it's a value. So dxy is a hom xy. This is incredible thought and very powerful. And these authors, Alyush and Simpson, they introduced, they picked up on the Gala paper and introduced this structure that is here and interpreted this as associativity. That's an important step. I worked on that together with a very gifted undergraduate that I had in its 4th year. And hopefully there will be more to come. But I'm slow, sorry. So, what we all know is a metrically enriched category. That's a richer structure than what we talked about before. Before here, we don't have a composite of F and G. We have only the ability to compare F and G with any candidate for a composite. That's the only thing we have. So it's not really a composition at all. But if you have a metrically enriched category, then of course you have a category you can compose, and the enrichment tells you that composition should be a morphism in the category, should be a contracting map. So for me, the maps of metric spaces are contractions, weak contractions. Also called short maps or Lipschitz 1 maps or whatever you want to call them. So we have a very strong level, metrically enriched categories. We have a very weak level, metrically enriched graphs, and what I term metagories. Don't crucify me for this invention of or enrichment of the English language. If it ever makes to the Oxford Dictionary, I will be very proud. So every metrically enriched category gives you a metric approximate category, a metagory. And since you have composites, this comparator function delta just becomes a metric via composition. Amazingly, this metagory gives you, in this fashion, a symmetric metric. So in these axioms for a metagory that you don't see, there's implicitly some symmetry in there that you can figure out. All right, so every Menger-Gala two-metric space, which has just points, gives you a chaotic metagory, so in which case you have from one point x to another point y just one morphism, and the delta is basically the same as the d. So an interesting case that these authors, Alyush and Simpson, discuss in detail is the metagory R to the n. We will come back to this in a second. We already saw that every metric category is a metagory. In particular, big things like the category of all metric spaces or of all Banach spaces with Lipschitz 1 maps are, of course, then metagories. And as a note, this induction of a two-metric space giving a metagory has a reflector, which is quite obvious, but we won't use that. All right, so now I do something strange when you see it at the first time. So I'm not dealing anymore with real numbers, but my values for the metric could be truth values, could be just 0, 1, could be all sorts of things. They lie in a complete lattice. So I replace the Lauvier quantile with an arbitrary quantile which has an order and a monoidal structure, and K is the monoidally neutral element. So for instance, you can reinterpret this in a probabilistic matter. In this way, it will be the same commutative unital quantile, but another philosophy in there. But I like also in particular, the truth values. So I like to read things even in Boolean logic. And this is certainly an important quantile. So if you take the coproduct of these two, which are isomorphic, so it's just the power in some sense in the category of commutative unital quantiles, then you get this quantile of probability distribution functions. Okay, so our V is a quantile which is nothing but a thin, symmetric, monoidal closed category. If you have such a thing, you can form the category of all V categories. So the V is not as scary as we saw this morning because it's just a thin category. Everything is quite easy. So even VCat is not as complicated as an arbitrary VCat. Inside VCat, you have these symmetric things where the hom xy is hom yx. Sounds very uncategorical, but it still works. And then this is symmetric monoidal closed again. So you can enrich, take this as your base and get your symmetric monoidal closed category of all metrically enriched categories. Intermediate stage is here. So let me remind you how you have your tensor product. So it's a cross product. And if you read this geometrically in real number, this is what a beginner would call the plus metric. And then you can do the function space. And this would be then the sup metric that you learn about in the first course in analysis. And of course, it's not as easy as this. So my functors, I actually didn't formally introduce this, but V contractive functors is like contractive functions on each Hom set. And for natural transformations, you just do what I say there. So what about this hybrid thing that sits between graphs and categories? Is it also a monoidal closed structure? So in this paper by Alyush and Simpson, they certainly have this. What is sorely missing is a notion of natural transformation between these. And if you have categories, you give your natural transformation on the objects. That's enough. Then via the commutative triangles that you have here, you have alpha sub f if alpha is your natural transformation. In a metagory, you cannot compose. So what you do, your natural transformation is a family of alphas for every f. And what you require, well, you can't really say that this diagram is commute, but you can say that the distance of this compared to these, 0. So if I write this down in quantalic terms, it's exactly this. And once you have required practice with this a little bit inconvenient tetrahedral inequalities, then you can prove, yes, it works. This is the right notion of natural transformation, and it makes Metagy symmetrically monoidal closed. All right. So enrichment of the category of statically enriched categories. It's enriched in itself, just like cat is enriched, since cat is a 2 category. And the second statement, what does it mean, is that horizontal composition is a contraction. Okay, great. So for a long time I thought, oh, there's no hope, because I don't have composition. If I define this, I need composition. Well, that's wrong. You don't need composition. So here's your typical diagram that you write down for the horizontal composition of 2 natural transformation. But you can do that also for metagories, because psi, for every morphism, has a morphism like this, in particular for phi f. And this gives you a wonderful, you have nothing. You have only this delta comparator, but horizontally you have a composition. And it makes, with some effort, V-metagories enriched in itself. And this is sort of a blueprint for a notion of 2 metagory. Now you just see what you have, and just like that is a prototype of a 2 category, Metagy V becomes the prototype for a V metagory, a 2 metagory. Okay, so now I want to talk. Okay, I want to talk about, can we embed a metagory into a proper metrically enriched category? Okay, so home is written there. And in order to make it a V-metric space, you have to symmetrize it. That's what we want. And then the composition becomes a contraction. So the strategy now is expand this to V-distributors, also called V-bimodules or V-cofunctors. There are lots of names, too many. Unfortunately, they're not the proper name, because it really should be called relators, because the relationship between functions and functors is the same as relations to relators or distributors. Okay, so how do we do this? First of all, here's the notion of V-distributor. So think of this as a compatible relation. And we just compose them as we would commit it into the category of distributors. The objects are the V categories. We have just more morphisms there, not just the constructors. So having more morphisms is the key to succeed. So this V is metrically enriched. You can compare 2 parallel distributors in the way you would expect this, and you get a separated V metric space for every Hom set, because V is separated. And so now you can form the Hom. So this is a V-metric category. This was just a metagory, but the right-hand side governs the whole thing. This is a V-metric category. It's good. So now we want to embed X into this, and Leonida told us how to do this. Unfortunately, it doesn't work always. So here comes now a problematic notion, and I mean problematic. It's really problematic, but it's a notion that works. So we call a metagory transitive if we have this equality, which basically says that why it is problematic. Well, first, the good news. If you have a V-metric category, it's a transitive metagory. But transitivity is not hereditary. So if you have something transitive and you take a substructure, you might lose that property. Even a two metric space, so a thin V metagory in general is not transitive. So transitivity you seem to have only when you have a lot of morphisms. Okay, so if you have a transitive category, things work amazingly beautifully. So you have your Leonida on objects as you expected, but then you labor through way through the morphisms. And in particular, this is an important step. You have an f from x to y, and then you have a b from y to w, and a c from x to w. And this is your Ioneda. It just even delivers this in the same order, and you get also natural transformations as you are supposed to. Another confirmation that the notion that we introduced for natural transformations is the right one, and objects are being mapped injectively. Same is true for morphisms if you have a separated metric structure on the graph linear embedding, and the thing that are constructed factors fit in a natural way. And maybe, I don't know whether I have space. I already said this.
Yeah,
2 minutes.
1 minute and then 2 or 3 minutes.
OK. So this is an interesting category, all the polygonal path in Rn. Rn itself is not transitive, but still you can manage to have an isometric embedding there. This is something discussed by Aliush and Simpson. So here are sufficient conditions for transitivity. And maybe I'll just go to the next slide. So one hybrid thing is for a fixed epsilon, you could consider that for any consecutive pair of morphisms, you have a candidate for a composite that is epsilon away from what you want. And you can also take the things that are at zero distance. And then you have things that are transitive. This is better. But of these, really only the things where for any consecutive things you have a candidate for a composite at zero distance, only that notion behaves really satisfactory for me in the sense that I can do